This is a brief look at what we call limiting reaction problems. These are problems that are frequently seen on tests and really do give a real-life look at what you might see in a lab. Because sometimes problems give you the masses of two reactants and asks how much product is formed from these two reactants. But you don't know which reactant is controlling the amount of product that's going to be formed. In other words, which reactant is in excess. It has a practical use in chemical engineering because ordinarily you want the expensive reactant, more expensive reactant, to be the limiting reactant, and the cheaper reactant to be the one that you oversupply, so that the reaction goes as much as possible to completion. So, you don't know which reactant is in excess in most cases. The other reactant determines how much product you're going to get. So, you start off as always with a balanced chemical equation. Then, you find how many moles of each of the reactants you have. And from that, you see which one you've got more than you need. And the other one, of course, is the limiting. So let's give you an example using moles. Suppose you have 2.5 moles of zinc and 6.0 moles of hydrochloric acid. In the reaction between the two, which one will be limiting? Well, first of all, you get a balanced chemical equation, which you see here. And this says that 1 mole of zinc reacts with 2 moles of hydrochloric acid. The equation tells you the ideal ratio of HCl to zinc is 2. Well, if we multiply the number of moles of zinc, 2.5, by 2, we get 5 moles of hydrochloric acid needed to react all of the zinc. You have 6 moles of hydrochloric acid, so you have more HCl than you need to react all the zinc. Therefore, the HCl is in excess, zinc is limiting, and the product expected would be 2.5 moles of hydrogen gas and 2.5 moles of zinc chloride salt. Let's do another example. If 30 grams of sulfuric acid reacts with 25 grams of aluminum hydroxide, forming water and a salt, identify the limiting reactant and determine how much water is formed. Well, we first of all start as always with a balanced chemical equation. And we need 3 moles of sulfuric acid to react with every 2 moles of aluminum hydroxide. That would form 6 moles of water and 1 mole of aluminum sulfate. This tells us that the moles of sulfuric acid needed would be 30 grams times 1 mole over 98 grams. That is, what do we have? We have in the 30 grams of sulfuric acid 0.31 moles of sulfuric acid. The moles of aluminum hydroxide, we have 25 grams. We multiply it, going in the mole hole, we multiply it by 1 mole over 78 grams, and we get 0.32 moles of aluminum hydroxide. Now, only 0.21 moles of aluminum hydroxide is going to be needed for 0.31 moles of sulfuric acid. Therefore, the sulfuric acid is limiting because we have about 0.11 moles of aluminum hydroxide in excess. So there's our balanced equation. The question is how much water is produced from the complete reaction of 0.31 moles of sulfuric acid. We now ignore the amount of aluminum hydroxide because we know we have an excess amount. So we solve for the mass of water, that's 0.31 moles of sulfuric acid, times the ratio 6 moles of water per 3 moles of sulfuric acid. We then multiply by the molar mass of water, 18 grams, to get back out of the mole hole, and we get 11 grams of water produced. Now, if you also knew the molar mass of aluminum sulfate, we could determine how much of that would be formed, because again, this 0.31 moles of sulfuric acid would form about 0.1 moles of aluminum sulfate. We would then multiply by the molar mass of aluminum sulfate, and we would certainly find that the mass of what actually reacted is equal to the mass of what is produced. That's the connection to the law of conservation of mass, which of course is the whole point of stoichiometry.